Welcome to the presentation on permeable pavements. My name is Alex Bartolo and I will be taking you through the presentation today. Section 1, Introduction, a brief overview on permeable unit paving. This is a typical permeable paving detail and it is important to note that the depth of the base material varies depending on site conditions. Different infiltration rates due to site soils and the loading the pavement will receive are two factors that strongly relate to the depth of the granular base. Starting from the bottom up, you have the native or emitted site soils followed by a geotextile layer that is intended to stop the proposed base aggregates from migrating into the native or emitted site soils. Following the geotextile layer is the subbase material, which is a larger aggregate with a 40% void ratio for the purpose of structural stability and infiltration of water. This subbase aggregate can pool water and works similar to a storage tank while the water infiltrates into the site soils if necessary. The next layer is the base material that consists of a smaller washed aggregate for low dispersion and permeability. Above the base material is the bedding material, which is yet another smaller aggregate material that helps set the unit paving. It is also permeable. The top layer is the unit paver and the joint material that consists of the same material as the bedding layer. All of these layers, when combined, form a strong system where the aggregates will not migrate between each layer due to their specific size and shape. Later in the presentation, we will revisit the composition of the base material, where I will identify the specific aggregates needed to build a proper permeable unit paving system. Section 2, Case Study, Guaranteed Rate Field. Construction of the Guaranteed Rate Field parking lot was very expensive due to the required stormwater infrastructure. Alternatives to standard stormwater construction practices were being assessed, and two designs were developed, one using a standard stormwater infrastructure and one using permeable pavement. The cost of traditional stormwater infrastructure was $300,000, which did not include the surface pavement treatment. The permeable unit paving option combined both the underground infrastructure and surface paving system into one cohesive system with a lower cost. Additionally, the permeable paving system infiltrated all water on site, opposed to draining the water to a municipal system like traditional underground infrastructure. Storage capacity is an important feature of permeable unit paving, and storage should be designed to accommodate an extreme rain event. For Guaranteed Rate Field, an additional 50,567 cubic feet of storage capacity was designed into the system to accommodate a larger rain event. The capacity is related to the depth of the subbase material, which in this situation was 14 inches of base aggregate with 40% void space, supplying 123,667 cubic feet of storage. For typical events, only 73,100 cubic feet of storage is used, but the system is made to accommodate an inevitable larger rain event. The existing soil conditions on site allowed for up to 14 inches per hour of infiltration, so the parking lot did not need to be connected to the municipal stormwater services. Site soils are an important part of success of a permeable pavement, so geotechnical engineers should be involved with the design of permeable unit paving systems. By implementing a permeable unit paving system, no extra infrastructure in the form of 44 inlets, over 3,000 linear feet of pipe, and a storage tank was necessary. Also, by exchanging a traditional stormwater system with a permeable unit paving system, there is an approximate savings of $2 million in underground infrastructure. The resulting permeable unit paving installation had no inlets, no concrete pipe, or storage tank, which led to an approximate cost savings of 15% versus traditional rainwater mitigation methods. The installed permeable unit pavers were two repeating bands of granite blend and dark charcoal colored Eco-Optilock pavers. The pavers were installed using machine for ease of installation, accuracy, and speed. In this instance, the installed pavers were treated with our classic finish, but we offer a variety of quality finishes, colors, and shapes beyond what was installed on this project. Eco-Optilock has the highest mechanical installation rates of any interlocking permeable paver. The patented L-shaped design makes the paver clusters easy to install quickly and accurately. Installation rates of up to 12,000 square feet per machine per day have been documented. This makes Eco-Optilock a very competitive permeable pavement that can be installed in even adverse weather conditions. Eco-Priora and Eco-Line are also available for mechanical installation. Section 3, Case Study, Buckingham Fountain. Buckingham Fountain was completed in 2009 and was paved with our Eco-Priora permeable paver with a series finish. The significance of this project is the desire to maintain the appearance of the existing pavement material, but it was failing and needed to be replaced. There was also a need for permeable pavers to improve the drainage on site. We were able to apply our series finish to our permeable unit pavers to closely match the existing color and overall appearance of the plaza space. The same natural stone material that was used to create the original pavement was applied to the face of our pavers in the form of an aggregate, which we refer to as series. The site receives constant foot traffic and is often used for filling, but it maintains its look and feel. Buckingham Fountain is the largest permeable unit paving plaza in the US, and it gave rise to a series finish that has now been used on a variety of projects since. Section 4, Manufacturing Standards, Reviewing ASTM Standards. ASTM standards require our pavers to have an average of 8,000 pounds per square inch of compressive strength, with a minimum of 7,200 pounds per square inch. The standards also require that our pavers maintain an absorption average of 5% with a maximum allowable amount of 7%. Height tolerances cannot deviate by more or less than 3 millimeters of the intended height in order to comply with the ASTM standard. At Unilock, quality is paramount, so we hold ourselves to an even greater standard than the ASTM requires. Additionally, our absorption average is 4% versus the prescribed minimum 5%, and our absorption maximum is 5% opposed to the minimum tolerance of 7%. These higher standards are significant as compressive strength is important during heavy loading and reducing the amount of water wicked or absorbed by the unit paver to prevent frost shattering. Section 5. Benefits, Infiltration and Pollutants. This diagram illustrates the movement of water through a typical permeable paving unit system. As contaminated water moves through the system, contaminants remain within the first 2 inches of the paving system and are removed by microorganisms. The water exiting the system is higher in quality, which is beneficial to humans and the ecosystem. This chart from the Interlocking Concrete Paving Institute, ICPI, design manual displays the increase in water quality as a result of permeable paving practices. Permeable paving fares well with most contaminants, but does fall short with de-icing chemicals that are commonly found in road salt. These de-icing chemicals make their way through the system due to their fine size. Overall, permeable unit paving systems do well at removing suspended solids and phosphorus, which can cause eutrophication when leaching into natural water sources. Eutrophication is common in agricultural areas where it creates dead zones and can be responsible for algae blooms. Section 6. Design, Materials and Laying Patterns. Before selecting a type of permeable unit paving, it is important to determine what you are trying to achieve. Consider what the goals of the project are. Does the site receive vehicular traffic, or is it a streetscape where wayfinding is important? Are there environmental factors that need to be taken into consideration? Is downstream erosion an issue, and what type of rain events will the pavement need to be designed to accommodate? What local regulatory requirements exist? For example, the Toronto Green Standard requires a solar reflective index of 29 or greater. Determine the site soils, as they will influence the base depth of the permeable unit paving system, and if water needs to be redirected to areas with higher infiltration rates. Lastly, what is the budget for the project? This can determine what type of finishes are available to you and whether immediate costs outweigh life cycle costs. Loading conditions are very important when designing a pavement, and the vast majority of the time they can be accommodated if considered during the design phase, ideally during detailed design. When the pavement receives a load, the base and sub-base components of the unit paving system carry the majority of the load. They must maintain strength in the presence of water for pavement stability. Aspect ratio is the relationship between the thickness of the unit paver versus its longest side. For example, our promenade plank paver is 100 by 300 by 100, having a thickness of 100 millimeters and a length of 300. It conforms to a 3:1 aspect ratio. As a general rule, for heavy vehicular loading, a 3:1 aspect ratio should be maintained. For light vehicular loading, a 4:1 aspect ratio should be adhered to, and all other paving sizes are considered pedestrian only. Laying pattern is equally important to aspect ratio. When designing a permeable unit paving system, it is important to implement a herringbone or double herringbone pattern for areas that will receive heavy vehicular traffic. Other specialized pavers such as Eco-Optilock and Bronte Street Paver are also acceptable due to their specific lockup features, but when in doubt, consult your local territory manager. These images illustrate the different sizes of various aggregates used in the construction of permeable unit paving. Take notice of the fact that these materials are all wash stone, free of fines. These tables speak to the different types of aggregates used to build a permeable unit paving system. Careful selection of base materials ensures that an installation can handle almost any amount of rainfall. Installing a permeable paver system above porous soils allows for rainfall infiltration, reducing runoff and flooding. Moist soils, even clay, allow for some infiltration, Soils with high porosity, such as sand, can have a higher infiltration rate than the actual rate of rainfall. For example, if it is raining at a rate of 2 inches 51 millimeters per hour and the soil has an infiltration rate of 4.5, 114 millimeters per hour, the soil will absorb water before it can run off. Even poor soil with a low infiltration rate will work. For example, a soil with decimal 0.25 inches or 6 millimeters per hour of infiltration will have complete infiltration after 4 hours of rainfall. Permeable paving is not a typical segmental pavement. Unilock recommends that a professional engineer design a site-specific plan based on available site information. Along with information provided in this presentation, Unilock offers all the data on our pavers necessary for a successful design and implementation of a permeable unit paving system. Section 7. Maintenance, Inspection, and Practices. Before providing maintenance on permeable paver systems, proper installation and protection during construction is required. The following are some things to keep in mind during construction. Verify the correct materials are installed. Hire contractors with experience installing permeable pavers. Review and approve all sub-base, base, and joint aggregate materials, and do not allow installation of dense graded aggregates. Prevent construction damage. Restrict vehicles with muddy tires from driving over newly paved surfaces. Do not mix aggregate materials. Refill joint material. Once between 3 and 6 months after installation, repeat as needed, approximately every 5 to 10 years. Lastly, avoid stockpiling of materials on or near the permeable pavement, such as topsoil and mulch. There are several warning signs and visual clues of common maintenance issues that must be prevented and addressed or remediated to ensure continued surface infiltration. These common problems can often be easily remedied by maintaining the proper joint aggregate level. Slow draining or runoff. This is easily spotted during a rainstorm as the surface should drain immediately. Ponding. If there is more than 22 millimeters of water after 1 minute of rainfall, maintenance is required. Surface cresting. Look for deposits of sediment and increase cleaning frequency. Weeds. Plant will not germinate unless there is a collection of soil or moisture, so ensure the joints remain open and free draining. Here is a list of some preventative and restorative methods. Regular surface cleaning significantly reduces the chance of a system clogging, which means other more intensive treatments will likely not be required. This type of cleaning would be considered preventative, but in the event regular maintenance has not been taken, restorative measures can be taken. These include power washing or lifting the pavers to remove their jointing aggregate. For more information on maintenance related to clogging prevention and removal, Unilock has a permeable unit paving maintenance guide. Use sodium chloride for temperature as low as 20 degrees Fahrenheit or -7 degrees Celsius. Calcium chloride should only be used when necessary when temperatures are below 20 degrees Fahrenheit or -7 degrees Celsius. Follow the directions listed on the de-icing product bag, but do use them sparingly. Only apply the minimum amount necessary to melt the snow and ice. Over-applying the product can result in damage to the unit pavers. Sweep and remove any excess de-icing chemical after the ice and snow melts. After the winter season, thoroughly wash the surface of the pavement to remove any remaining excess de-icing chemicals. When using plowing equipment, it is important that they are equipped with plow scrapers and blades made of high-density plastic to reduce the risk of damaging paver joints and the surface of the pavement. While scraping the surface without this protection will not compromise the structural integrity of Unilock pavers, it may affect the aesthetic of the surface by leaving behind rust marks and further damaging the finish. In contrast, a rotational snow broom can be used to remove snow safely from the paver surface. Unilock suggests establishing a best practice maintenance program to ensure longevity of the system before restorative action is required. I will briefly take you through a maintenance program. After the snow melts, March 1st to April 15th, begin using a broom, blowing equipment, or a rotary brush to clean the surface of the unit paving. Give special attention to areas used to stockpile snow. Once this is complete, replenish the joint aggregate. Every 5th year, vacuum or power wash problem areas and refill the joint material. Late spring, April 1st to May 15th. Again, use a broom, blowing equipment, or a rotary brush to remove organic material from trees and shrubs. Collect any additional debris, especially from areas that have been mulched or planted with annual flowers. Replenish the jointing aggregate material as necessary. Late fall, October 15th to November 30th, once again, clean the pavement using the same methods and replenish the joint aggregate material as necessary. Make note that various factors will affect each project's preventative maintenance timeline, so they must be individually reviewed. Section 8. Products, finishes, sizes, and colors. Our classic finish is tried and true. It is frequently used as an economical option due to its durability and familiarity as it has been on the market for some time. Our classic finish is made with through-mix concrete that contains larger aggregates for durability, which can also be seen on the surface of the unit paver. Enduracolor utilizes the same durable concrete as a classic finish, but is then topped with a face mix to provide a range of textures, colors, and lasting color. The top of the paver also has a finer finish, so larger pieces of aggregate are not visible. Our Elegance line is made using wet cast concrete, whereas other products use a dry casting method. By wet casting the pavers, we are able to offer seamless textures and colors, as well as form finer features into the pavers. Additionally, our wet cast concrete unit pavers have a higher compressive strength to form an even longer lasting pavement. Our Eco Optilock has been used for years due to its durability and adaptability to any situation. It's made with our classic dry casting manufacturing method and is formed in an L shape for increased lockup. Because of these characteristics, it is economical and can withstand heavy vehicular loading without movement or cracking. DuraFlow is a permeable pavement specially designed with rapid clean technology. Cleaning in the correct direction allows for easy extraction and replacement of jointing aggregate. Treo Smooth is new and provides designers with a permeable paver option that can be installed in a random pattern. It also has a smooth, modern aesthetic. With the success of our Promenade plank paver line, we introduced Eco Promenade to supply the design community with a plank-style permeable option. This product is available in a face mix and can be used in heavy vehicular situations. Our Tribeca cobble paver provides you with a unique cobblestone appearance in our durable and exclusive series finish, while also being permeable. LEED, Leadership in Energy and Environmental Design, is a green building certification program that recognizes built-in-class building strategies and practices that have a positive impact on the health of occupants while promoting renewable clean energy. To receive LEED certification, building projects satisfy prerequisites and earn points to achieve different levels of certification. Unilock products can help with their certification goals. DriveCell is a reinforced soil structure product that enhances the performance of pavement structures. I will now play a short video from Iowa to further explain how it functions.
DriveCell reinforced pavement structures. This is Phil Perzia from Perzia Geosolutions. I am a geostructural engineer that specializes in reinforced soil structures. In conjunction with Pete Chiron, the president of Iowa, I will be discussing DriveCell reinforced soil solutions. DriveCell is a stiff, three-dimensional geocell that was developed to help stabilize and reinforce unpaved driving surfaces. DriveCell tiles are 500 by 500 millimeters square with various thicknesses of 30, 40, or 50 millimeters. DriveCell is so strong that you can drive on it empty. We developed the innovative solution of lowering DriveCell to reinforce the pavement structure for maximum performance and durability. The addition of DriveCell within pavement structures maximizes the strength, stiffness, and resilience. To help understand this, we will discuss how pavements fail, how DriveCell works to prevent failures, why this is important, where we can use DriveCell, and the benefits that DriveCell provides. Pavement structures are strong in compression but weak in tension. They can fail in different locations, from different causes and mechanisms, but ultimately they fail in tension. DriveCell stiff geocells strengthen pavement structures by combining the best of both worlds from geogrids and flexible geocells by reinforcing and confining. This results in the maximum strength, stiffness, and most importantly, resilience for flexible pavement structures. DriveCell can be used in the base layer on decent subgrades and directly on weaker subgrades like a snowshoe to reduce the pressure on the subgrade. DriveCell can be added into conventional unreinforced pavement structures to significantly increase their strength and performance. Or you can take advantage of the strength increase by reducing the thickness to reduce the excavation and granulars while maintaining a similar or greater strength when compared to the original unreinforced section. Here is a comparison of the wheel load distribution for a flexible versus rigid pavement. In a flexible pavement, DriveCell maximizes the stiffness to increase the load distribution and maximizes the resilience to increase the durability. Together, these maximize the performance lifespan. Ultimately, this reduces the maintenance costs and minimizes the life cycle costs. For permeable pavement structures, the base and subbase are typically composed of open graded granulars. The design priorities are structural first and then drainage. A rigid and impermeable concrete base layer is a mistake under a flexible and permeable concrete paver's driving surface. The concrete should be replaced with drive cell. As shown on the very right, 2 layers of drive cell can be used in pavement structures, one on the base and one on the subgrade to further increase the reinforced strength and minimize the excavation and granulars. The original concrete base for this driveway was replaced with drive cell. Drive cell can be used on the roofs of parking garages to improve performance, especially at transitions, and to reduce the weight of the granulars. Tension cracks typically form at transitions from one type of pavement to another. Installing 2 layers of drive cell along the transition helps smooth the transition and prevent cracking. Too often, pavements and curbs break up around catch basins. Installing drive cell helps tie this area together to reduce costly repairs. Pavement structures often deform and crack over culverts. Installing drive cell under the culvert helps spread the load and reduce the excavation required. Installing another layer above the culvert in the pavement structure helps prevent deformation and cracking. Drive cell maximizes the long-term performance of pavement structures for maximum benefits. During construction, the excavation and granulars can be reduced. Plus, the installation is quicker and easier. This results in overall time and cost savings. Maximizing the resiliency maximizes the durability. This means more wheel passes, less maintenance, and smooth transitions. Finally, using drive cell has direct and indirect environmental benefits, including reducing export and imported materials, reducing truck traffic and related air and noise pollution, all while reducing the overall carbon footprint. Thank you very much.
The next portion of this presentation will be done by Jennifer Drake. Jennifer is an associate professor in the Department of Civil and Mineral Engineering. Her research group works to develop and improve blue-green grain stormwater infrastructure to mitigate and minimize urban flooding, helping our cities become more resilient and adaptive to a changing climate.
Hello, my name is Dr. Jennifer Drake. In this presentation, I will be discussing maintenance practices for permeable pavements. Permeable pavements have been built and used across North America for almost 40 years. But despite this long history, there still are a number of challenges associated with implementing this technology. And these challenges are pervasive not just for permeable pavements, but for a wide range of low-impact development or green infrastructure technologies. First is the legacy of past failures, especially associated with the pilot or first generation of these technologies. Some of the early systems were constructed without the same understanding of hydrology, improper use or maintenance, and even the design and construction practices has evolved as the technology and the community, the professional community, has advanced. And the history of these early adaptations, where a lot was learned, but there were some mistakes made, still resonates with today and creates a lot of hesitation with selecting permeable pavements as a pavement of choice. The other hesitation that regulators often have is the issues regarding or related to private ownership. How can we guarantee that private owners will maintain their property? If we're relying on this infrastructure to provide stormwater management practices, we need to ensure that it is functioning. And that is why having good operation and maintenance plans and having a suite of options and in terms of how to maintain your permeable pavements is really critical to address the challenges associated with private ownership. Finally, the next challenge is, of course, maintenance. And as this technology has grown and expanded, the experience that is available in the professional community and the contracting community has grown. And we don't have the same lack of experience we have, as we'll see in this presentation, a range of equipments and systemized practices that we can use to maintain these systems. Another challenge associated with implementing permeable pavements is accounting for costs. Permeable pavements, by their very nature, are two infrastructure systems simultaneously. They're a pavement system, a part of the transportation or pathway network, and at the same time, they are a stormwater system, providing stormwater on-site quantity and quality control. These are two costs that previously were addressed and dealt separately in a project and now are being combined. And so that leads to the perception that they may be more expensive when in fact you're getting two services instead of having two separate infrastructure systems. There's a lack of education awareness and misconceptions related to how permeable pavements behave continue to persist. One of the most common misconceptions that I encounter in my profession is what happens during the winter. And as we've seen through our research, permeable pavements actually provide a great deal of stormwater management and actually reduce the risks of slips and falls through less ice formation. If you look at the picture on the side here, you can see closest to us is some impermeable interlocking pavement, and then to the far end is actually permeable pavement. The permeable pavement, when the snow and ice melts, it infiltrates, and so the pavement actually becomes dry more quickly. The impervious pavement closer to us, that water hasn't drained, and when the sun goes down, may refreeze and become ice. Lastly, we have issues with quantifying performance. And I'm going to show a couple examples so we can see what benefits we get and how obvious they are for permeable pavements. So again, in this image, we can see a second time the quantity control that is being provided by this interlocking permeable system. The interlocking permeable pavers allow water to infiltrate, and so we don't have any direct surface runoff during a rain event. And you can see the asphalt in the back, we have ponds, we have surface runoff starting to occur. Here, we can look at a short video that demonstrates, again, the lack of direct runoff that we have during a rain event.
It's really raining now and no flow from hydromedia. And a lot of runoff from asphalt.
Permeable pavements will still produce discharge if they have an underdrain, a design that is very common throughout all of Canada. And that discharge water, even if it is connected to a downstream sewer, is going to have improved water quality. As we can see in the photo here, we have water from that same rain event that we just saw in that video. And the samples were collected in moments in time. The top shelf is runoff from asphalt at that parking lot. And as you can see, we see this effect called the first flush effect, where we have a release of pollutants from all of the dirt and debris that was on that surface that then is mobilized when runoff occurs. In contrast, permeable pavement discharge, which was released and collected from an underdrain at the base of the pavement underlying the aggregate, it's actually gone through a filtration process. And so those suspended sediment, that dirt and debris, is not present, and we do not see the first flush effect. And you can see quite clearly the quality of the water looks much improved. So when it comes to operation and maintenance, for permeable pavements, it really starts with construction. We need to make sure that permeable pavements are constructed properly from day one so that they are performing at the way they're intended to. And when working with permeable interlocking concrete pavements, or PICP, as I'll use in this presentation for short, one of the first things that we need to make sure the contractor understands is that PICPs do not use sand. Conventional interlocking pavements will use cement or construction sand for bedding and joints. We do not use this material for permeable pavements. We should be using a coarser aggregate that's going to allow us that space that we need for water to infiltrate. It's also important that erosion and sediment controls are well maintained and installed correctly. If we have construction runoff depositing silt and clay and dirt where a permeable pavement is going to be constructed, or on the surface or on the aggregates as it's being installed, this is going to mean that we don't get the high infiltration capacity that we want from day one. So making sure that sediment erosion control is done well is absolutely key. The best way to do this is, of course, through site inspections, preventing construction mistakes, making corrections before things proceed too far and they become expensive to repair. Last tip that I'll have here is, of course, that we should also consider our staging and sequencing. If we are going to have materials like landscaping materials, we don't want to be using or depositing that material on the permeable pavement, again, because it may cause clogging. So if we are going to have to stockpile material, we want to think about having tarps or things that are going to prevent that migration or contamination to the permeable pavement. So how do we assess whether or not a permeable system requires some maintenance? And most of the time, this can be addressed through very simple inspections. This can be done either before a rainfall event or during a rainfall event. If you're visiting a site before a rainfall event, things that we should be looking for are material that is accumulated in the joints. Content or material that's not that aggregate, whether it be sediments, leaves, pine needles, cigarette butts, trash, that is all material that is going to be causing clogging and is going to be reducing the surface infiltration. We can see in the photo here some dirt that's in a permeable pavement joint that actually becomes quite caked and quite dense that almost seals the joint, preventing water from being able to infiltrate. If you see the presence of vegetation in a permeable interlocking system, that also suggests that maintenance is probably due. Vegetation will typically only be able to establish if there's already organic material and sediments present. Otherwise, the material is too coarse, it's too open, and it's not a good growing environment for the weeds. The other very effective way of assessing whether a permeable system is functioning as designed is, of course, to do an inspection either during or immediately after a rain event. Do you see surface ponding, water at the surface? If you do, and especially if you see it persisting after the rainfall event, this suggests that the pavement has lost its infiltration capacity, there's accumulation of sediment and dirt and debris in the joints, and is in need of some maintenance. And a very simple visit during a rain event will basically tell you everything you need to know. Another way for planning or knowing when we need to do maintenance is to track changes in surface infiltration over time. And this can be done through a very simple single ring infiltration test. We get a ring that we prep with something that's going to allow it to seal to the surface, whether it be we use either plumber's putty or clay, and we place it on the point of interest on the pavement. Any sort of openings along the joints are sealed, and then we apply a known volume of water. Measuring the time it takes for this water to infiltrate is a data point that then we can repeat, once a year or once every 6 months. And this will let us see and then also anticipate when we are going to require maintenance for our pavement. In the second half of this presentation, I'm going to talk about some research findings that my group has done at the University of Toronto, assessing the different options that we have for restorative maintenance. In this study, we wanted to directly compare different approaches for maintaining a clogged permeable pavement. So we have an experimental test pad in our research group, and it's a generic interlocking herringbone pattern constructed fully to scale. And we clogged this system in a controlled manner so that each cell of the test pad received the same quantity of sediment, which would allow us to then directly compare different technologies and approaches for maintenance. So to clog the pavement, we collected street sweepings from GTA municipal yards and measured, sieved, and prepared the material so that it could be applied directly to the joints. And you can see the little vials of our sediment all lined up ready to be applied. This was then over repeated intervals directly applied to the surface, and then the surface was wetted to prevent any wind erosion. And we did this over a series of weeks until we were able to basically accelerate or simulate, extensive clogging across the entire surface. In the images here, we can see what the test pad looked like once it was clogged. You can see all that dirt and debris. We left one cell bare, saving it for a follow-up study. And you can see it in the far distances in both images. You can see just how much cleaner that surface looked. And so we had this consistent clogging with no unknown variables, ready for us to then bring in maintenance equipment and try and restore the surface infiltration. So we started with looking at street sweepers that have been either looked at the past or street sweepers that we know that municipalities or contractors would have access to. So as you can see here, these are the first two types of street sweepers that we tested. A vacuum sweeper, where you can see we have a vacuum head at one side of the vehicle and brushes and rollers that direct sediment and materials to that size. And then the second is a regenerative air sweeper that actually has air circulation taking place. And so you have air being forced down and air being sucked up on either side of the vehicle. Regen air sweepers are quite common because of their improved air quality or because they have less air quality effects. And so many municipalities, this is their fleets today, or their replacement vehicles are our regenerative air street sweepers. We also tested a waterless mechanical street sweeper. And as you can see in the photo here, this is not the typical mechanical street sweeper that you might see, say, at a construction site. This is a top of the line, modern mechanical street sweeper, which have been developed, I think, very much to compete with regenerative air street sweepers. And so materials were removed fully through mechanical brushes and brooms, dislodging material, and then moving it to a conveyor belt that deposits it into the vehicle hopper. We also wanted to look at the types of maintenance that might be useful, say, for an individual homeowner or small installation. And so we did manual pressure washing followed by vacuuming with a shop vac. Finally, we tested a specialized equipment that has been developed specifically for restorative maintenance of permeable interlocking concrete pavements. So this is a Typhoon. It is a two-staged maintenance. First, materials dislodged with a high-pressure blower that's connected to an air compressor. And then, with the aid of a vacuum truck, the material is vacuumed up. So let's just take a quick look at what the Typhoon looks like when we're actually vacuuming the material. The advantage with this as well is that it does have the maneuverability that it may allow it to get into different areas that a vehicle like a street sweeper would have more difficulty with. And of course, it's been developed in the US just for PICP. Okay, let's talk about some results. What did we see? Well, to understand or measure the effectiveness of these different maintenance approaches, we did that single ring infiltration test after construction, after the clogging, the accelerated clogging, and then after the maintenance treatment. And the nice thing, or the positive thing that we saw, is that all of our approaches restored some surface permeability. So there are a lot of ways that you can restore a clogged parking lot. The most effective system, kind of not really a surprise, is of course this pressurized air and vacuum technology, this two-step system that's been specifically developed for restoring neglected or severely clogged permeable pavements. And this one was able to restore our pavement right back up to its pre-construction or post-construction infiltration rate. The second best performer was then a vacuum street sweeper. In some places, it did restore surface permeability back to post-construction levels, but there was a great deal of variability, and we'll take a look at this in the next image that I'm going to show in a second. Surprisingly, the waterless mechanical street sweeper and the regenerative air street sweeper had about comparable results, and they weren't even that different in some cases to manual pressure washing followed by vacuuming. And so this shows that depending on what type of vehicle is available, you could use one or the other interchangeably, but it also states that speaks to the fact that you will probably need to go over it multiple times. To control the variables in this experiment, each vehicle was limited to only a single pass. So the systems that didn't restore all the way back to post-construction levels, we most likely or almost certainly could have gotten better performance if we had allowed the vehicles to go over the surface more times than just the single one. In our second figure here, we can actually see some of the spatial variability that we observed as we compared our infiltration measurements that were taken at different points across the cell. And as you can see, some of the systems were very uniform, like the high pressurized air, very consistent service no matter where you are. But the vehicles, especially since we limited them to a single pass, and our cells are relatively small compared to the size of the vehicle, you can actually see where there are higher levels of restoration taking place and lower levels. And these are connecting to the direction or relating to the direction that the vehicle is traveling, or in the case of the vacuum sweeper, the location of that small vacuum head. And so this shows us that if we want to make sure that we achieve uniform restoration, we may want to, especially with street sweepers, where you kind of have rectangular vacuum heads or suction heads, go at least twice and do a hatch pattern. So go, one way on the first pass and then perpendicular or 90 degrees to that, so that you're getting both joints. You're going over both joints regardless of their orientation. And this should improve the restoration that you achieve during the maintenance. So a few other comments or lessons learned that we have from this study. First is to remember that regardless of the maintenance practice that you are applying, whether it be washing, sweeping, or vacuuming, it's going to remove the material in the joints. And so that joint material will need to be replaced or topped up following the maintenance so that you don't have holes along the joints. You need to replace that material. Next, the second thing is that, of course, the material that is clogging your surface, as it changes, that's going to affect the success of the maintenance applied. So in this study, we actually saved a cell and we repeated the specialized equipment on a pavement cell that had been clogged not just with street sweepings, but also street sweepings mixed with soil collected on site. So soil that could have, blown in over time, and it had a fair bit more clay and silt in it and much more cohesive. And the effectiveness of the maintenance dropped significantly. And so in the presence of cohesive, high organic, fine silts and clays, maintenance is going to be more challenging, and you may need to do more passes or spend more time to get that restoration that you're trying to achieve. With this, it lends itself to think about run-on. Permeable pavement systems are often designed to have impervious areas draining to them. But a drawback or a consideration for that type of design is, of course, more stormwater means more sediment. And with more sediment will mean more frequent maintenance required. I've already commented about the benefit or the recommendation of doing multiple passes. And lastly, maintaining early. This study is a worst case scenario where a pavement has been left to be clogged severely. Implementing the maintenance earlier in the life cycle in an early and routine practice will drastically increase the effective life of the pavement. And we did a similar kind of follow-up study on this, and we were able to see that the pavement's life would be increased by 50% by implementing more regular maintenance, even with a poor performing or even with the regenerative air street sweeper, which is not designed specifically for PICP maintenance, but is very readily available. So that brings us to the end of this presentation. I must acknowledge, of course, our funding provided by NSERC, the ICPI Foundation, in-kind contributions from TRCA, Lafarge, Branton Bricks, and of course, I could never not acknowledge the research students, Jody Scott, Jeff Marvin, 𝐸𝐨𝐻 𝐸𝐵𝐻, and 𝐸𝐨 and Adam Crooks, whose work really brought all this together. Thank you. I look forward to answering questions during the live event. And if you would like to follow up with me, my two emails are jen.drake@utoronto.ca or jennifer.drake@carleton.ca. You can also follow me on Twitter @stormwater_TO. Thank you very much. Bye.